Today we're going to be talking about slope fields and Euler's method. And I actually start with an introduction with a differential equation. So a differential equation is an equation that involves a derivative. This is a first order differential equation because I have a first derivative. So how I solve a differential equation is, I'm going to rewrite it for us so that I have it to work with. I'm going to use separation of variables, so I'm going to multiply both sides by dx. So I'm separating out any y's and then anything that has a dx. So y is separated from the x's. Then I'm going to take the integral of both sides. The integral of y, dy is y. The integral of our right side is x cubed minus 2x squared plus 3x plus c. Now they give me this initial condition that f of 2 equals negative 3. So I plug in negative 3, I plug in 2, and I solve c, and for c I get negative 9. You can go through that algebra. I'm not going to bore you guys with that algebra. So then my expression for f of x, since they asked for f of x, let's give them an f of x. X cubed minus 2x squared plus 3x minus 9. Now, if you can't solve the differential equation, so for example here, I don't know how to solve that. Actually, we do know how to solve that, but it's a little bit harder to solve. I want to draw a slope field, okay? And for the following differential equation, and draw the solution curve in at negative 1, 0, and then we want to solve the differential given that 0, negative 1 is on the curve, okay? Let me adjust that because I want to make sure that I have this right on here. Okay, so a slope field is just showing the little pieces of the tangent lines at different points. So meaning if I plug in 0 for y, so anything on the x-axis. So if I plug in 0 for y, I get dy dx is equal to 0 minus 1, which is a negative 1. Since there's no x variable, it's same for all of the x coordinates. So I have a negative sloping, and I look at that like I kind of draw a 45-degree angle line. What these are little like tangent lines at those points. That's what those are standing for. Now if I plugged in 1, I get 0. I guess I could have put 1 there too. There was no dot there. Now if I plug in 2, 2 minus 1 is 1, so I have a positive sloping line. And again, these are just little ideas of what the tangent line looks like at each one of those points. If I plug in negative 1, I get a negative 2. So make sure that's a little bit steeper than your 45-degree. And then when I plug in negative 2, wait, that was negative 1. So negative 2, I get a negative 3, so even steeper. So now I want to draw in the solution curve through 0, negative 1. I picked that for a reason. So as I go, here my slope is negative 2. And then I go to the right, going to the right, my slopes are even steeper, so it looks something maybe like that. And then I curve over, and I go to a slope of 0. So that's an idea of what our solution curve looks like. I had a slope of a negative 2, so that's how I know I would go there, because that's technically a negative sloping. and then I'm still negative sloping. I have technically a horizontal asymptote, but you'll see that in a minute. You don't go past those lines. Now they want us to solve the differential equation given 0, -1 is on the curve. I'm going to separate my variables. I know that's technically in the next video, but we've already seen this in our AB class. I integrate both sides, and I get the ln of the absolute value of y minus 1 is equal to x plus c. Now what I do is I have to look and see what these actually no, let's convert this first. So I have e to the x plus c is equal to the absolute value of y minus 1. I'm going to do a couple things at a time here. This e to the x plus c, remember that this e to the x, that's like saying e to the x times e to the c, so I can make that a new constant out in front. Now we need to figure out whether or not I need these absolute value signs. So this still always needs to be positive. If you plug in -1, the inside would be negative. So I have to do a negative of a negative number. Or, looking at that a different way, I have to do 1 minus y. Now I plug in my initial condition, 0 for x, e to the 0 power is 1. If I plug in -1, I get a 2. So my equation ends up being C2 is 2, e to the x equals 1 minus y. If I solve for y, I get 1 minus 2 e to the x. Now, if you notice, that's some exponential curve sloping down, horizontal asymptotes 1. So I wanted to show you guys how this curve relates to this curve, which relates to the slope field. So I think that that's an important thing for you guys, a concept for you guys to realize. Okay, Euler's method. For us BCers, this is a new concept. So what Euler's method is we use numerical approximations of our solutions to our differential equation to approximate the value of the curve. So what's happening here is we have a tangent line. So I have an initial point, and I'm trying to approximate a value on the curve, but I can't solve the differential equation. What we can do is we can use little tangent lines. So what I do is I draw a little tangent line. And then from this tangent line, I use another little tangent line. And then I use another little tangent line. And if I were to carry this curve up all the way, I'm using this value here, that y value is going to approximate what that y value is. Now, we need these increments, these dx increments, to be really small. Okay, so we're going to be using, a lot of times they're like 0.1. Sometimes if you don't have a calculator, there's something like 0.5 because that's an easier number for us to work with. But really all you're doing is you're writing little equations of tangent lines to approximate a y value. That's what Euler's method is. So what you do is you start at an initial point. So you start at some initial point and you use this formula. Really what this is, guys. So for years I couldn't remember Euler's formula. All it is a tangent line. So we have y equals some y1 point plus my slope delta x is this change in x. So the change from that point right there to some other x1 point. So really all you're doing is you're using a tangent line approximation. Okay, if you remember this piece and remember the chart on the next slide, you should be fine on it. And this requires a calculator, so if you don't have your calculator, please pause the video and get your calculator. Sometimes these are going to be non-calculator, sometimes they're going to be calculator, just because of these small increments. I used a calculator on this. I wouldn't see an easy way to do this without a calculator. So I have my differential equation. This is a differential equation we don't know how to solve. And we have an initial condition. So we have an initial condition. We need to go from 1 to 1.4 using 4 increments. So how I figure out my delta x is 1 minus 1.4 minus 1, where you're going, where you came from, how many increments you have to get 0.1. Now to get your delta y, or your change in y, this is your change in x. To get your change in y, you plug it into slope times by your change in x. So I plug in 2 times by 1 plus 2, all of that times by a 0.1. And that ends up being 0.4. Now to get your new x, what you do is you take your initial x, you add it to it the change, because I'm going over a certain amount. So I have 1.1. To get your new y, you take your initial y, you add to it your change to get 2.4. Now these are your new x's and y's. So now I'm starting at the point 1.1 and 2.4. Your change, your delta x is still the same, and you have to find your change in y. So my change in y in this case is 2 times by my x value plus my y value, which was 2.4, times by your delta x, and for that I got 0.46. Again, I just found that in my calculator. Your new x, I'm going over another increment of 0.2. I'm adding an increment to this. I'm adding my delta y to my initial y to get 2.86. Now these are our new initial x, initial y. The delta x stays the same. I've never seen it change. That's not something they're going to throw at us. 2 times 1.2 plus my y value, which was 2.86. Don't forget to multiply by your delta x. And there I get 0.526. So my next x value is 1.3. My y value, when I add 0.526 to this 2.86, I get 3.386. So add you go your next increment. I'm sorry, this is my new initial point. I'm sorry, I got distracted. My mind went wandering. You do not even know where my mind went. I was thinking about something completely random. 2 times 1.3 plus 3.386 times by 0.1 equals 0.5986. So my new x is 1.4. That's what I'm trying to estimate. 1.4. My new y, I take this, my delta y, add it to my delta x. I get 3.9846. And that is our approximation. Okay, so all I'm really doing here is I'm doing little tangent lines. I'm starting at this point. I'm doing little tangent lines until I get to 1.4. Now the next one. So different differential equation. Your point you're starting with now is 3, 4. My delta x, I want to get to 2.6. I'm starting at 3, 4 equal increments. So this is now a negative. So my delta x is negative, and that ends up being the same for everything. Hopefully you realize it's negative because I'm starting at 3, going backwards. Now again, this is just a matter of plugging in. Okay, I'm not going to bore you guys with the plugging in. I'm just going to give you the values. Double check and make sure you guys get the same values I get. I've done this a few times, so I'm hoping that over the past few years, these values are matching up. So again, I'm just plugging in this x and this y into my differential equation times by negative 0.1 to get these values. I just don't want to bore you with that work. Again, plugging in 2.8 plus 2 times 2.03 times by dx, and I get negative 0.686 and 1.344. Here I get negative 0.5388. My new delta x is 2.6. Remember, that's what I wanted to get to. And then my new y is 0.8052. So that's my approximation. So this is approximately 0.8052. So that is a review of slope fields, differential equations, and our new topic for BC, which is Euler's method. And I'm thinking in my head, I think this is the first new topic that we had. So welcome to some BC topics. All right, everybody. That is all I have for you. Please make sure that you are doing what you need to do. I don't know how I could end this. All right, everybody. I will see you soon.